identify these, I would say, coefficients, A1, A2, B1, B2, and so on, and one additional one we don't care about now at the beginning. So this is the only formula which I will show, but this is the key for the entire presentation. The question is, if I get a graph, a function, how can I get these parameters A0 to AN and B1 to Bn? So far, so clear?
Yeah.
That is the entire theory of Fourier transformation. That's true, but should be fine.
What is the W doing there?
The W, yeah, these are. You have the standard or the base frequency, the W times X, the base frequency, and you always increase the frequency by a factor. So you start with a frequency W, then the next term is using the frequency 2 times W, then 3 times W, and this will be shown in the next slide what it means a little bit. So, but always remember, we need to get these coefficients, because if you have these coefficients given, you can reconstruct or redesign the function. And how does it look like? If you have here a function f from by x, this function can be separated into different kinds of sinus and cosine functions with a different frequency, always multiple frequencies, and this is shown here automatically. So we have to wait a moment until it starts again. So wait a moment. So this is a function which we would like to analyze. Come on. And this function should be separated into these different kind of signals. Here you see it, they are added according to this formula. Again, you see the same formula as in the first page or first slide. And getting these parameters, the amplitudes of the different signals here, these are the coefficients which we would like to determine. On the other hand, you can also use these coefficients to generate the function, the red function f by x, again reverse. Understood so far? This is now happening. This is one of the machines which used this process to generate a function. That is a tidal machine developed by William Thomson, later Lord Kelvin, and they had the task. The tide of the Thames is important for the harbors, because if the tide is too low, you might not get the ships into. So to know what is the tide height, let's say in 1 month's time, would be quite important. So knowing the frequencies of the tide, so the parameters of the tide, then you can generate the function, the tide height, at a certain point of time. And exactly this is the machine doing here. It simulates also the periodic rotation of the moon, of the earth, and so on. But it can predict all the tides for different places for the next up to, I think, 2 years. 2 years. And it's located in the Science Museum at London. So this is an example for a harmonic synthesizer. That means generating the function out of the parameters. Of course, this is not a desktop device, and I would like to have it, but I cannot afford. So there are some variants available, but you can hardly buy it. Now coming to a, I would say, poor man's solution. Oh, first of all, where is Fourier transformation also important? It's not only looking for tide heights. I'm pretty sure a certain amount of people in this room have already been Fourier transformed. You know where?
Communication theory.
Pardon me?
Communication theory.
Yeah. No, you personally might have been Fourier transformed. Your body.
In such a machine?
Yeah, in the nuclear tomography, the data measured is a Fourier transform of your body. So getting the picture back is a reverse Fourier transform, and you see it's quite important. Yeah?
It is in ERM, which means magnetic resonance
yes.
used magnetic resonance identically in computer tomography.
Yes, yes. Your computer tomography is slightly different.
I was teaching this
Yeah.
machine.
Yeah. It's slightly different. It's a radon transform. It's a little bit different. Yeah, but you're right.
Yeah, it's CT, computer tomography, and magnetic
Yes.
resonance. It's used.
So I'm pretty sure several people of you have been already Fourier transformed. Luckily, you did not need to be. The process back was not required. Okay, but it's not only Fourier transform. It's cryptography. It's used in audio analysis, in sonar technology. It's used in optics, even in the data compression like JPEG. It's also part of it. And there you see the importance of this methodology. So it's a widespread approach, but it's also an approach where many students are really scared of. Many students had to attend these courses, and then they forget, because it seems to be too complicated. But I think it's worth to look into this topic. So always, if you have a function which you need to get analyzed, where you need to identify influencing factors, there you use the Fourier transform. Another example is, perhaps somebody of you have heard about the app Shazam. Yeah? Shazam is an app where you can use your mobile, which is and music is running in the radio. You can let the Shazam listen to the radio, and within very few seconds it gives you the title and the interpret of this of the running music. And it's done by doing an analysis, also a Fourier analysis of the audible sound, getting a fingerprint and looking for the fingerprint in a database and immediately bring it back, the result. So another application. Or for the old school people, I'm also an old school people, if you have a stereo system at home, an audio system, you might have seen these equalizers, where you see it going up and down. It's nothing like the Fourier transform for some frequencies. Okay, this is, as I promised, I would say, not the today's Pullman's harmonic analyzer, but I would say the first desktop analyzer in this of this type. That is the so-called Marder analyzer, and it was invented in the year 1909, and it was produced by the company Sterzel in Vienna, I think Vienna, at least at Austria. And we only know about 119 of these items has been built, not more, because the latest serial number known so far, and I have been in intensive contact with Professor Fischer, who is the person who knows about this. And you see it's quite small compared to the earlier tidal machine. This box has about this size. And you see only some wheels, some toothed wheels, some strange items here, and some, I would say, bar where this item can run. It looks a bit strange, but we will show later how it works. Another producer or manufacturer who was quite successful with this is the company Ott. They started with the production of these systems without an agreement by Marder at about 1929, and they came up with a quite amount of variances of these systems, and I will go in a little bit deeper in this talk about the variances of these types of analyzers. What are the main parts? Here in the top you can see how the system is built up. That's an original copy from an instruction leaflet. You see here the function fx, which you typically trace with this tracer. You go in this direction and back, and with this mechanical, I would say, instrument here, you get some values here. What is very special, we will show the operation also interactively. Here on this wheel there is a standard planimeter mounted. So, Paul, you have no one, no? So one planimeter, and so if you start the operation, you read the planimeter value here, then you go forward across, you trace the curve, and then you go back, and then you read the parameters here again. And you subtract the values, and then you have the coefficient, one coefficient, A1, B1, and so on. And what coefficient you have identified depends on the wheel which you are using. So for the next coefficient, you take a different wheel from here, put it there, and do the same process again. And for this, you get another coefficient. And what we will show later, there are two holes in this wheel where you need to put the planimeter or connect the planimeter to, and depending into which hole you put it, you get the sine or the cosine parameter. That sounds really strange, but it works. So typically these systems are sold in such kind of boxes where you have all the parameter. This is called a carriage. That is this carriage carrying these, I would say, this angled device, which is running into a bar with a slit. And on top you have these wheels which you exchange for each and every parameter. And here you, in some storage boxes, you will even find a planimeter, which is sold together with them. Or it could be left out, and you have to buy the planimeter by yourself separately. Very often, for these smaller setups, you also have this wooden table, this white wooden table, shown here, because the planimeter is running on this wooden table on top. In several of these boxes, these wooden parameters be quite long, which I will show later. So perhaps now you would like to see how this thing operates. And he is a famous inventor of these presentations, so we had been in contact up front. So I will show how this is really working. And this is also available for all of you. It's on the USB stick, but you can use it also on the internet. So I will show this. I will use the automatic mode. I will take the wheel 1, put it here. You see that we have the tracer here. We have this wheel mounted here, and the planimeter is shown here, the wheels, and we have shown here the value which is showing given by the parameter. Now we start to go around the curve. You see the tracer is following the curve. You see how the planimeter is moving. And this is a mechanism how the harmonic analyzer is working. Going back, and now we have the value for the first coefficient. If we now go for the, we can choose a different different wheel, so we get a coefficient for a higher frequency. We can start, and you see the even the trace, this trace here of the planimeter tracer is looking already completely different, and so you get different values at the planimeter. So you get the second coefficient. So far we have only measured the the cosine parameter. If we switch to the sine parameter for the same wheel and start again, it's showing a different value. And the curve is also looking a little bit different. And in that manner you can use it. Of course, this is now an easy function, the sine function. Andres has made it like this, that you can even draw manually. And you can even use different functions here.
There's also a tight table in it. For Scheveningen for today. Yesterday.
Pardon me?
There's also a tight
Ah.
graph in it, the last one. If you select the last data set, it's the tights. One day of it.
Yeah, we can start this.
It's these 3 days.
Yeah.
So now we can go outside and check it.
Yeah. So you see, you can identify the coefficients for the tiles, and then you can build up the tile heights with a more expensive non-desktop version in the science museum. So,
Just a question, is the yellow wheel, is that a representation of the frequency of a wave?
yes, the size of the wheel gives the correlates to the frequency.
Frequency.
Yes.
The yellow one is that.
The amplitude you get, but whether you pull the planimeter here in this cosine or in this sine hole, you get the parameter for sine or the cosine, and the size of the wheel. Perhaps I can go for more. It's more interesting even for a very small one. There you see the higher frequency. It's looking for the higher frequencies.
So the smaller the wheel, the higher the frequency.
Yes.
Okay.
Yeah, I think I'm missing something though. The first example was a sine wave. How
Yes.
come you got more than a single coefficient?
Pardon me? For
The first example was a sine wave, so you should have had only one non-zero coefficient.
yeah, but the values were close to zero.
Okay.
But in fact, you showed first the cosine values,
Yeah.
they all were very
Yeah.
little.
Yeah. To be honest, Andres and myself, we struggled. The accuracy of this model is not 100% correct, like in real life. So, don't rely with your ship going into the harbor on our measures. Okay. Now I have shown the simple MADA analyzer. So that is a standard system. So here we are now digging a little bit deeper into the components. And what I already mentioned, here you see this hole for the cosine, and here the hole for the sine, where you had to put the planimeter in. Obviously, everybody knows the cosine is only 90 degrees away from sine. That is the reason, nothing else. So here all the gears are numbered so that you can easily identify for which parameter or which coefficient the gear is used. So this is the gear for the coefficient A1 and B1. For some of these coefficients, it's difficult that they are running directly in these two bars. Therefore, for example, for the coefficient 8, you need an intermediate. Below this tooth wheel, there is at the bottom another tooth wheel which is getting into the tooth bar. So, and now you see already one difference here. In the animation, we had only one wheel to mount. Here, we can already mount two wheels in parallel. And this is a significant difference. There are analyzers available which only have one plate where you can put the wheels. And other analyzers have two plates in parallel. You can use this, that you can with one run with the tracer over the function, that you can get two coefficients in parallel that you only need to run once. So it's a kind, only half of the time you need to get the coefficients. Looking a little bit closer to the hole plates. At each hole, there is a small number, not so good visible here. Here it's, for example, a 2, because you need to know in which hole do I need to put the corresponding wheel. Because they have a different size, they need to be placed in a different area because the tooth bar is at a constant distance. Therefore, for setting up, you have to check which wheel do you need to put where. The double hole plates has been introduced only by 1941.
Excuse me,
Yes.
Detlef.
Yeah.
There is something that resembles a 4 in Roman numbers upside down.
In the middle.
A bit above.
Where?
In the middle.
Yeah. Yeah.
What is that for?
Wait. It's coming. It's coming. This is a very important part, which I'm very proud of about the 4. Come to that point later. Now you see also the number of wheels. You have you can look for more frequencies. So in the earlier box you saw only 9 wheels or something like this. And there are analyzers available with up to 48 gears. 2 times, that means 96 gears. And here the idea is that you can use even the same wheel for the same parameter number 1.
The sine and the cosine.
Could be.
For the sine and for the cosine.
Yeah. But of course, I would be very much interested to have this kind of device, but I'm quite sure they are not so often available via eBay. So coming to another.
So what is the material of this?
Brass. As per my understanding, it's brass.
I think we saw these at Bob Otney's house.
Pardon me?
One of the last times we went to visit Bob Otney's.
I had not been there. Yeah.
So it must be somewhere in his collection that's being auctioned.
Yeah. But he has this kind of things. Yes, I've seen this, but I had not been there. Another variant for this harmonic analyzers. We only showed this part of it. You have one tracer where you can put one carriage where you can put 2 planimeters in parallel. This system shows 4 carriages which are combined to each other. They are completely connected like a train, a rail train, because here is a rail, and you can mount to each of these carriage 2 planimeters in parallel. With this setup, you can have 8 with one trace of the curve here. You get 8 coefficients simultaneously within one run. This planimeter has been introduced 1941. We know it exactly because this photo is available with Professor Fischer, and I have copies of this photo, and it says 3rd of April 1941. This photo is visible in several books, exactly this photo, because the photo by the company Ott are numbered. So even in I think in villas at home, at least. And the wooden table, of course, you will ask some carpenter to provide this to you, because it will never fit into this box.
But tell us, who was in such a hurry that you needed this optimized instrument?
Unfortunately, we don't know who bought this, because all the books by Ott showing the deliveries of the products are only starting 1942, so 1 year late. So because in the electrical domain they had a need of Fourier transforms, and if they want to perform a lot of calculations, then it's beneficial. But that's an assumption. We are not completely sure. Definitely not for private households.
What's the serial numbers on that one?
2157,
They made two, wow, they've made a lot before.
Yes, I will come to that point later as well. But we are quite sure, we assume that this might be a one-off, because the modification to which I have shown with the carriages has been introduced only 1 year later. Because somehow this setup, I built it up on my at my home, it's a little bit unstable. And with this optimization, you get it more stable.
Later, when you are finished, I will explain you. I assume this machine was built for the German Navy.
Could be as well.
For acoustic torpedoes.
Yeah.
And I explain you later, in the 60s, when satellites were up, the US Navy had put many buoys around in the Atlantic. And they made harmonic analyzing and were able to say this ship or this submarine, not only the type, but exactly one. Like the voice of every person is different. Every ship
Has its own signature.
Has its own signature. And in the 60s, the Russian battle cruiser was in London officially, and there was Lionel Crabbe, which was a real experiment foreman from the British Navy. He had the job to look for the ship's crew, because the Orchonikidze cruiser had a very low acoustic signal. So Crabbe died and never appeared again. So we don't know if Crabbe was returned and captured by the Russian, or if he was killed. But Crabbe in the 60s never came up again.
Okay.
Never was showing up again.
Very interesting.
Yeah, yes. See, so stories are coming. But I'm pretty sure installing this on a ship would be a nightmare because of the movement. Okay. There's another variant with the different types of analyzers. You have seen the graphs here, which could have been analyzed. With this extension arm, you could increase the size of the function of the graph, which you can analyze by about a factor of 2. This is also part of my machine, so this is also belonging to this.
This was done to increase the accuracy.
No, not the accuracy, but to increase. You see here, it's a comparable small graph, which you can reach with the tracer. With the extension, you could achieve a longer, analyze a longer and a higher graph.
Then still isn't the objective more precision, because the graph is periodic, so.
Yeah, it depends. If you draw it in a smaller manner, you might even need to redraw before it can be used in the system. When the system is bigger, the accuracy is higher, of course, but also you can use bigger graphs or larger graphs. So, but there are even more complicated attachments. Unfortunately, I'm not owning this kind of things, but I think, if I remember right, Bob almost had also one of this. You could put another device on top of this carriage. You see here the planimeter again, and with this you can determine even more complicated integrals, the so-called Stieltjes integral. How does it work? Instead of this rotating wheel, you put this frame on top, and with this frame you run with one person or one hand along this trace, and with another person take this length and run along this curve. With this you get a weighted integral over this curve. And since you need two people to do this in parallel, one is operating here, concentrating that you're not missing the curve here, one is concentrating here. This could even be enforced by a special, I would say, schablon templates, mechanical templates, where the movement of this device is forced by the mechanical guidance here. So this could then be operated with one single person.
So you could put a sine function.
Pardon?
You could put a sine or a cosine function in there, and then you don't need your 80 wheels.
Yeah, no, but this is a special integral here, where you would like to have a special additional term. I think.
But I'm saying, if you have the Stieltjes one, you don't need.
Yeah, then
the
you.
analyzer anymore.
No.
You can use harmonic analysis.
No. This is not a sine function, but typically it's a.
Sine function.
Hmm?
You could use
It could. Yeah. So there had been another company who went into this business, that I call it a late adopter, that is Stanley. They started with the manufacturing of these harmonic analyzers in 1950 and stopped in 1965. And they had three types of it. And they only built 55 to 60 as per my knowledge. So one version is a single hole, one version is with a double analyzer, and one with two set of gears. This is a visible order of material which is available with me. And also the source is given there. And now summarizing this a little bit about the manufacturing of these Marder-Ott analyzers. Stürze started at this time at 99, ended the production at about 1930, and in total around about 200 devices had been built up. The company Stanley started very late. They produced only about 60. The company Ott started 1929, and they stopped the production in about beginning 1970s, and they produced less than 600 as per our knowledge. So that means this type of harmonic analyzers had been produced about less than 900 items, but not the big ones in total. The small ones, the big ones, the medium ones, all over the world as per our knowledge.
Didn't the American companies produce everything similar?
I have never seen something in this style. They have produced perhaps analyzers, but not the Marder-Ott type, as per my knowledge. If there are additional information, I'm keen to correct this. So this is more or less my story. Any question and answers?
That number 4 in Roman numbers.
Okay.
Still
Start with the first place already.
So here you can see
there, yeah.
it again,
Yeah.
and it's simply the force carriage of my system. If you look here, you have the one is noted with 4, one with 3, 2, 1.
Ah, okay.
So that's because when you build up the entire system, you need to know how they need to be connected. And on all different single components, it's clearly mentioned this need to be mounted on this carriage. So it's one, you cannot, should not exchange it. So the 4 is the fourth carriage of this setup.
Thank you.
But you have to buy 8 or almost 8 planimeters.
Yes,
The same planimeters or?
you can use different as well.
Oh yeah.
But you need planimeters which are having not
What do you say?
a magnifying glass, because you need a planimeter which has a kind of drawn something like a nail, or which you can put into the small hole. But of course, if you take different planimeters, you always need to consider the different coefficients for the planimeter for the correction, but it's possible.
It was very interesting what you say. You have spoken about calculating of teeth. And
Yeah.
the greatest calculator for teeth stands in Bremerhaven.
I know, the Gezeitenrechenmaschine.
It is 10 meters long and 5 meters high.
Yeah, I know. And I plan to visit this.
Yes.
Big pictures.
This is also
Any additional questions? Huh?
When you trace a curve, then the length of the period of this curve has to be a fixed length, I think. Can
No.
you measure this fixed
No,
length?
no, it does not need to be fixed because it only needs to be period. So a period. So if you go, yeah, wait. This one. It's important. The length is not fixed here. It needs only to be in the range of the tracer. But it's important that it's periodic. That means the starting point needs to be on the same height than the end point. So you need to make it, I would say, if it's not periodic, you need to make it somehow periodic. Because you run the tracer from here across, then going back on this line.
So, but when going back, the tooth wheel makes a whole round or 2 rounds or 3
Yeah.
rounds, and so the length of the line where you go back is fixed when you make a whole turn of the tooth wheel.
No, because if you go in this direction with along the curve, it's also not going beyond. So this is compensated in that sense.
I tried to help you.
Yeah.
First of all, thank you very much, Detlef.
Yeah.
But you're 50 years too late with this story.
Oh.
Because I needed 50 years ago. I'll tell you why. You are invited here in the Netherlands.
Yeah.
And we are living below sea level,
Yeah.
behind the dikes.
Yeah.
The south part of the country has a lot of large sea arms,
Uh,
where the sea tide comes in. And we have built there storm surge areas before. When I was a student, at the end of it, and later on I worked on it, we also got those curves, what you see over there, because it is the measured curve by equipment like Peter was saying, at sea. And the curve is in fact a combination of one sinus, and a smaller sinus, and a very small sinus. They were the longest formulas in my life I have used. And you see now with the wheels, that gives a certain frequency. So the wheel, what fits is checking from how many times do I fit in, and what is my amplitude and my factor belonging to that frequency. So they use this type of equipment to analyze, in fact, that if you have this frequency for that wheel occurs. So you get very long formulas of alpha sinus and beta cosinus and sinus, etc., etc. Why do we need that? So we had large formulas with all those different frequencies and heights in it. We had to reduce the entrance of the eastern scheldt to reach at the end, 50, 60 kilometers further, a certain tide level. That was the criteria. The question was, how much do we have to reduce? And the reduction has a different impact on each of those sinus and cosines. And we know them of each. So we first have to how do you say that, to analyze, to take the natural wave in parts of different sinus and cosines, and that for each cosinus or sinus we could calculate what the reduction is, and then we show them back together, and you get a tide at the end.
And what you just mentioned is exactly to understand the influencing factors on the function and signal.
Yeah. So we took it in parts, an enormous amount of sinus and cosinuses, all different amplitudes. We know if you reduce it that much, that will be the impact for each individual one. And then we throw them back again, and then we looked at the end, 50 kilometers further, what the final tide is. And if there is really coming a large storm, then we close the complete opening. So you are 50 years too late.
Oh, sorry, I complain to my parents.
Already planning to upgrade the thing.
Sorry?
Already planning to upgrade the
Yeah, but that's something.
That's a different story.
That's a different story. That's for something, a new presentation, how you can do that.
I can tell you the nice thing was, and that was part of the result of my study as a student, so I Rijkswaterstaat had those analyzing equipment. I had never seen it at the time, but they did it, and they gave me the formulas in the huge box with all those cards in it. You remember that time? And I was reducing those systems. There were two different systems. You had the implicit and the explicit differential methods to be used. Don't ask me what it was 50 years ago.
Yeah.
And they used one method, and I used the other one. So we could compare the results of both calculations. And that was more or less comparable. But as a student, you want to do something strange, of course. So I started reducing the opening further. And then the relative normal sinus at the end start changing in a double one.
Mm-hmm.
So it was not that curve, but it was go up and get what a double butt.
Mm-hmm.
Yeah. And it was just a little bit more than the opening which was expected to be built. So we got in panic, thought, hey, do we make a mistake that we go instead of this curve end up with a very strange curve at the end? Yeah, so they also started investigating with their calculation method by further reducing the opening if they would reach the same, and that happened. So we were very close to a very strange phenomena at the end of the CR to realize. We just a little bit higher, so nothing happens. But that was coming out of all this type of analysis.
And you did it 50 years ago?
I did it 50 years ago.
So by your calculation, now is the upgrade coming from what?
It isn't climate change.
It's climate change that doesn't exist at that time.
No, okay, I misunderstood that.
Okay, it was marvelous, let me say.
Yeah.
Thank you very
Thanks.
much.